Thank you for letting me know. Somehow the microphone was off. So we are going to talk about IUPAC naming, then physical property, then would be how to prepare these compounds and what are the chemical reactions for these compounds. Carboxylic acid has high priority, so you would start from the carbon that has the carboxylic acid functional group 1, 2. So you have ethane for 2 carbon. You drop the E and add oic acid. So for 2 carbon is going to be ethanoic acid. For 3 carbon is going to be propanoic acid. 4 carbon would be butanoic acid. So if you have butanoic acid, 1, 2, 3, 4, anything that does not take a number, and if is other functional group or a branch, you have to name it first and give the location. So we have an amino group, the carbon number 4. So it would be 4-amino butanoic acid. For this 5 carbon acid, which is the pentanoic acid, there is a phenyl group on carbon number 3, so it would be 3-phenyl pentanoic acid or 3-methyl butanoic acid. Okay. The carboxylic acid always starts with carbon number 1. Unsaturated acids, so you have to give the location of where the carbon-carbon double bond is, and then instead of using, so in this case we have 6 carbon, instead of using hexane, you would use hexene, but you have to give the location of where that carbon-carbon double bond is. So you are using hexene instead of hexane. Instead of saying hexanoic acid, it would be hexenoic acid. But the carbon 3 takes the double bond, so it's 3-hexenoic acid. Anything that does not take a number after you select your longest carbon chain, any alkyl group that doesn't take a number, it would be named as a branch. What is this E or Z? It's coming from if you have a carbon-carbon double bond. You could have cis or trans, like CH3, CH3, H, and H. Both CH3s are on the same side, so this is going to be called cis. If you have CC double bond and CH3s are on the opposite side, it would count as trans. So we have cis and trans. Now, if the 2 groups that are attached to the carbon, one of the double bonds, are different from the other side, if these groups are not the same, so you're not dealing with the methyl hydrogen on both sides, then you don't use the term cis and trans. Instead, you are using E or Z. Z similar to cis and E similar to trans. In this case, you have to give priority. The priority is either 1 or 2. So if you have, you're dealing with this first element attached to carbon that carries the double bond. So this is going to be carbon attached to one side, hydrogen. Obviously, carbon has higher priority compared to hydrogen, so carbon would take 1. On this side, you have carbon and carbon. So we cannot decide based on the first carbon. So you have to move further away. So you have a hydrogen attached to this carbon, but in this case, you have a carbon attached to carbon. It's not that this is heavy group, it's just what is attached to this carbon. So the ethyl group would take priority 1 and methyl group would take priority 2. Same priorities are on opposite side, and that makes this like looking like a trans or E. E meaning they're on the opposite side, and Z on the same side okay? Same site, like a same groups or same priority on the same side or same site. So it stays on the same site. Okay. So trans is similar to the E. Aromatic acids, those are the acids that benzene ring carries the carboxylic acid functional group. Of course, inside the ring, there is no possibility. There is no cyclic acid at all, because then it would be like too many bonds. If you have a CO double bond, that's okay, but you cannot have OH here. So we don't have cyclic carboxylic acid, but we could have aromatic ring attached, or cyclic ring can attach to COOH or carboxylic acid functional group. For the benzoic acid was the parent name. We learned about this in chapter 16. That's the benzoic acid. The carbon that carries the benzoic acid functional group is going to be carbon 1. So if that is carbon 1, then that's carbon 1, 2, 3, 4. Automatically, this is going to be like 4 amino, because it's NH2, 4 amino benzoic acid or para amino benzoic acid. You have carbon 1, 2, 3, but the logic is to go to the side that is going to be closer to the other group. So you go clockwise. This is the 2-hydroxy or ortho-hydroxy benzoic acid, paramethyl benzoic acid, or we have the naphthalene with 2 benzene attached. Dicarboxylic acid, they have 2 carboxyl group. It has to be beginning and the end of the carbon chain. So you have in between, you have 6 carbon, 1, 2, 3, 4, 5, and 6. So it's going to be hexane. Instead of oic acid, you would say dioic acid. And then you start from the side, numbering from the side that is closer to the branch. So basically 1, 2, 3, 4, 5, and 6. So bromine would be on carbon number 3. You have to number from the side that is closer to the branch, because for the carboxyl group is not going to make a difference. It's beginning and the end of the chain. So 3-bromo hexane dioic acid. So di meaning that you have 2 carboxylic acid attached. If you look at the structure for the carboxylic acid or the formic acid as the simplest, formic acid or methanoic acid is the first member or the smallest member, and the hybridization of the carbon is a sp2 hybrid. The bond angle about 120 because it's sp2, and the bond length is 123, okay? 1.23 angstrom, and that is carbon-carbon for double bond. Okay. So we have sp2 for carbon, but sp3 for the oxygen. Carboxylic acid, forms resonances, and also it forms a dimer. The dimer, we already know that carboxylic acid can form hydrogen bonding, so that is going to increase the boiling point. But when it forms like a dimer, not only forms hydrogen bonding, but also it makes the molecule act like double the mass. The molar mass is like doubled. And that gives unusually high boiling point to carboxylic acid. So carboxylic acid, they do have very high boiling point. Melting point for carboxylic acid, it depends on the number of double bonds that they have. If it's saturated or one double bond, or mono unsaturated, or polyunsaturated, di-unsaturated, the more a carbon-carbon double bond you have in the molecule, the lower the melting point is going to be. That happens for unsaturated oil versus saturated or fatty acid, or animal fat versus plant. So if it's saturated, melting point could be very high and it's solid at room temperature, and the pi bonds is going to lower the melting point. So if you have like olive oil, it would stay liquid even in the fridge with the low temperature. But if it's basically, if it freezes or if it goes to solid, that means it's not pure. Or the temperature of the fridge was much lower. Solubility, like dissolves in light, carboxylic acid with less than 5 carbon would dissolve in water, but if they have higher than 5 carbon or higher, is not going to dissolve in water, and the solubility is going to drop significantly right at 5 carbon. pKa of the acid, that means the acidity of the acid, which is based on the equilibrium constant. Ka is the equilibrium constant for the acid, weak acids. And pKa, if you take negative log of the Ka, you get the pKa. pKa of the acid like could be around 5, which is much stronger compared to pKa of alcohol. And the reason for that, if you go back to like chapter 1 and 2 of the organic book, it does explain about the resonance. When alcohol loses a hydrogen, is going to change to alkoxide, and alkoxide, there is no chance for resonance. But carboxylic acid, after losing a hydrogen, would change to carboxylate ion, which can form resonances. And that's the reason for higher acidity for carboxylic acid compared to alcohol, because what is left after losing hydrogen is going to be more stable. As a result, it requires less activation energy, or the energy diagram also supports that. It's more stable. It's going to stabilize by the resonance. How would the substitutions is going to affect the acidity of carboxylic acid? Electron withdrawing group would always increase the acidity. So if you have acidic acid versus chloroacidic acid would have higher acidity or lower pKa. Lower pKa value means stronger acid. Dichloro is even lower, and trichloro. For a compound that you have like a butanoic acid, the closer the Cl group is to the COOH, is more effective in terms of the electron withdrawing group. So it's going to be a stronger acid. So if you have 4.5 to pKa for 4-chloro, for 3-chloro, it drops down to 4.05. And then for 2-chloro, it drops down to 2.86. So the closer the electron withdrawing group is to the functional group, the stronger the acid is going to be. For aromatic carboxylic acid, aromatic acids, you have electron withdrawing group would increase the acidity. Electron donor group is going to lower the acidity, and you can use this as a base, the benzoic acid, and compare everything else. This is electron donor group, acidity decreased. Okay, electron withdrawing, electron withdrawing, electron withdrawing. And for all three cases, you have NO2 as electron withdrawing group, but the numbers are different. So if it's in the meta position, it's not very effective. Remember, activating and deactivating groups, if they are in the ortho and para, the effect is more significant. So if it's meta position, it's going to lower the acidity, but not as much as the ortho and para. If it's in the para position, it's going to be more effective than ortho position. But if it's in the ortho position, if it's in the para position, it's going to be more effective than the meta position. But if it's in the ortho position, because of the distance, it's going to be the most significant effect. So if it's in the ortho position of NO2, the acidity is going to be the highest. Okay, I'm actually going to stop here and continue with the reactions of the carboxylic acid later, and other properties. So carboxylic acids, since they are acidic, they can lose hydrogen. And in order to lose hydrogen, you have to bring a strong base. Since it's carboxylic acid, you can use either sodium hydroxide or potassium hydroxide to remove that hydrogen. And it would change to, because it's acid-base reaction, you end up with salt and water. So you have the salt and water. And now to name the salt is just like naming salt. Metal comes in first, name of the metal would come in first, and then you name the anion, which is the carboxylic acid. So if you have the salt of the acid and you add to acidic solution, it would regenerate the acid. We have used this in the past for recrystallization of benzoic acid. If you add like sodium hydroxide, it would go to the salt form and it would be in aqueous solution. But if you add HCl or concentrated HCl, it will precipitate. Because it's basically, the weak acid going with the strong base, it would give you salt. But when you have the salt plus strong acid, the strong acid would take the metal ion from the strong base and leave the anion alone. So when you are naming, as I said, you are going to bring the name of the metal first. So we have potassium, and then we have 1, 2, 3, 4, 5 carbons. So it would be pentanoic acid. But instead of the ic acid, you remove the ic acid and add ATE. So O would stay, just that part. So O would stay. So you have the pentanoate, and there's a chloro on the third carbon. So it would be trichloropentanoate. But metal would come in first. Some properties of the acid, they can form salt with sodium hydroxide, potassium hydroxide, or lithium hydroxide. And the salt of those are soluble in water. So basically the soap is the soluble sodium salt of the long chain fatty acid. So when the salt forms, as it acts as a bridge between the oil and the water. So if you hydrolyze the fat or oil, which is basically triglyceride, is going to give you glycerol. Basically is the cleavage that is taking place. Okay, so the cleavage is going to be between carbon and oxygen single bond. Carbon oxygen single bond is going to break, and you're adding water. When you're adding water, this bond is a polar bond. You're adding H and OH, so you would add H to one side and OH to the carbon. So basically, but because it's in the basic solution, the OH is going to be deprotonated, and it gives you the anion or the salt. And then the salt is the fatty acid salt or the soap. If you are using like sodium hydroxide, it would be sodium salt of the fatty acid, or potassium salt of the fatty acid. Carboxylic acid, they can react with strong base, and if it reacts with strong base, it would change to salt of the carboxylic acid. If you bring in sodium hydroxide or potassium hydroxide, the salt that is forming is the sodium salt or potassium salt. Any compound that contains sodium or potassium is going to be soluble in water. So basically, if you have carboxylic acid in the mixture, when you're trying to extract, you add sodium hydroxide. Okay, when you add sodium hydroxide, it's going to react with the carboxylic acid, and it changes the salt of the carboxylic acid, which is water soluble. It will go down to aqueous layer. When you're dealing with extraction, you do have two layers, the organic layer and the aqueous layer. And it's not always the top layer organic and the bottom layer aqueous layer. It depends on the density of the organic solvent that you are using. If the organic solvent is less dense than water, then that is the case. The aqueous layer would be the bottom layer. So when the salt forms, it's soluble in the aqueous layer and it will go down. But if you bring HCl, if you add HCl to the salt of the acid, it's going to regenerate the carboxylic acid, and it would be insoluble, so you can actually recover the carboxylic acid. Spectroscopy of the carboxylic acid based on the functional group of COOH, CO double bond would have a peak around 1700, 1715. And then you have the OH, that for carboxylic acid, OH is going to have a peak between 2500 to 3500. It's a broad peak. So it starts from 2500 and it goes to 3500. And it kind of, you see these spikes here, these are not spikes from NH, because you learned that in chapter 12 and 13. These are from the CH groups, the CH from, sp2 or sp3, but it's going to overlap with this OH bond from carboxylic acid, which is very strong, very broad peak here. And then the CO double bond also is going to be broad. The CO double bond, if it is conjugated, it is going to be lower than 1700, but if it's not conjugated, it's going to be higher than 1700. So it depends on the structure of the molecule that you're dealing with. Like this one is conjugated, it's going to be less than 1700. But if you have a compound that carboxylic acid, that CO double bond is not conjugated, it would show up at higher than 1700. Questions? NMR for carboxylic acid, it's the easiest one because it's always like out scale. The carboxylic acid would show a peak between 10 and 12, and sometimes they say 10 and 13. It doesn't bother me much, but as long as it's out to scale, or says offset by 2 ppm, so then you know that you have a carboxylic acid. For mass spec, the fragmentation that you're looking for, it can be alkene, cleavage of the alkene. You must have like a at least 3 carbon, more than 3 carbon in the molecule. If you do have more than 3 carbon, alkene would form, and you would have that lose of the alkene as a rearrangement, as a result of rearrangement. So the carbon after the 3rd carbon is going to be cleaved off, and you get a carbon-carbon double bond, formation of alkene.